All right, here we go. This is lesson 4.1 as we covered it in class. If you need it for review or if you were missing and you never did see it. We're just starting out with kind of a simulation. It reads, how many free throws would you need to see Mrs. Gallus, this little lady right over here, shoot before you could be confident guessing her free throw percentage? That's her true historical free throw percentage. We're going to use this applet at statsmedic.com, and you can go there. You can just do a search on statmedic.com and applets come right up, and you can just select from the ones that are available, and there's Mrs. Gallus right there. Just make sure you choose it as an individual. All right, so we're going to click shoot to shoot free throws one at a time. So this is actually a simulator. Keep track of the results in the table. When you think you know Mrs. Gallus's true free throw percentage, stop recording. All right, so here we go. One shot, one make. All right, so how many makes are one? And let me see if I can actually make this work. All right, and that's 100%. We'll shoot again. All right, now she's 2 for 2. So 2 and 100%. And we'll do it again. Whoops, she made 2, and that's going to be about 66.7%. Just keep going. Oh, another miss. All right, I don't know why this is doing that, but so that's going to be 50%. All right, this is not a very big sample size, so I don't think we can really go with where we're at yet. We need to add on a few more. So now she's 3 out of 5, and that's going to be 60%. All right, now we're going to just do 5 more in rapid succession. And you can go pretty quickly here. So 1, 2, 3, 4, 5. All right, now she's 8 out of 10. So that'll be 80%. Let me get that fixed. See, there's my go back. 80%. All right, and we're supposed to stop when we think we've nailed her true free throw percentage. I'm going to do 5 more. So get up to 15. So 1, 2, 3, 4, 5. All right, that's 11 out of 15. And that's going to be 73.3%. I'm going to guess around 75%. All right, so how could we make this more accurate? Well, let's pause and I'll write it out for you. All right, the way that we could make this scenario more accurate would be to just make Mrs. Gallus throw more and more and more free throws, because the more you do it, the more you kind of overcome what you might see in the short term, where she might get unlucky, or she might just have a bad day, or she maybe just does way, way better than she normally does. She will eventually reach or get close to her true percentage and stay there. Okay? There's a name for that, and that is the law of large numbers. And we'll define that more precisely in a little bit. So again, the truth is Mrs. Gallus has an 80% probability of making a free throw. So let's interpret that. So if Mrs. Gallus shoots a very, very large number of attempts, she should get close to that true probability of 0.8 or 80%. Now, in statistics, when you start with phrases like very, very large number, you're talking sort of like the infinite. You know what I mean? It's just, we're talking a huge, huge, huge number. So yeah. So click until you get 50 free throws. What percent did Mrs. Gallus make out of 50? And let's just see here. So let's go up to, I guess the next thing is 20. And we're accelerating this. Oops, I went too far. I think I'm just going to go all the way up to 50. And there we go. she made 38 out of 50, which is 76%. So 38 out of 50, and that's 76%. So even that didn't actually reach 80. We would just have to keep going on and on and on and on. So here we go, that's 76%. All right, if you were to do this simulation again, would you get the same percent, and why? All right, no. If we do this simulation again, or if I do it and you do it and somebody else does it, every group of 53 throws will give different results. They should give different results. They might not, just out of pure coincidence, but we would expect them to show some sampling variability. Sampling variability shows up later in lesson 4.4, so we'll look at it when we get to that, but you can get the idea. In fact, in the next section right here, you can see this dot plot, and I'm going to change this up a little bit here, this scenario, because it's really, we're not interested in 30 students in a class, we're interested in Mrs. Gallus. But you can see that she's had some good days, 90%. She's had a few bad days, 66 and 70%. But you can see that this is kind of clustered around her true free throw percentage, which is 80%. All right, so I made a little bit of a change to this sentence. Here are the free throw percentages from 30 simulations of Mrs. Gallus. So this is actually her doing groups of 50 free throws, and she's done 30 of them. That's a lot of free throw shots, but every 50 of them is a dot. So this is 50 free throws, and the average for this group of 50 was 84% for her success rate. Up here is 90%, and so on. So explains what the dot at 70% represents. So it represents one simulation of 53 free throws in which Mrs. Gallus made 70% of them. It's this guy right here. Okay, so the very last thing before we take a break, use the results to estimate the probability that Mrs. Gallus, an 80% free throw shooter, would make 70% or less when shooting 50 free throws. So let me get an interesting color. Let's try that one. All right, we're talking about 70% or less. So it's this. I'm not talking about anything to the right of that, just 70% or less. And we're seeing 2 out of 30, which is approximately 0.067. All right, let's just take a quick break at this point. All right, I hope you enjoyed that brief intermission. We're going to go to the next page and talk a little bit about these learning targets. So the first one is just a kind of a definition of probability. I am going to feature a different one. I mean, it's kind of the same, but I think the one that I'll show you in an upcoming video will actually kind of be a little bit more useful when you apply it to answering probability questions. So we're here, And so the definition that we're going to use for now for probability, and that's the proportion of times the outcome that you're interested in occurs in a very, very long series of trials. All right. That's like talking about Mrs. Gallus shooting many attempts at free throws and eventually landing at 80%, which takes us to the law of large numbers. All right, the law of large numbers is your learning target number 2, and that just says if we do something many times, that means sort of indefinitely, like repeat things forever in a kind of theoretical way, the proportion of desired outcomes will approach its probability. That's kind of how we figure out probability for strange events. Okay? And then parts of a simulation. All right, that little girl that was shooting baskets, I guess that was supposed to be Mrs. Gallus. That was a simulation. We didn't actually watch Mrs. Gallus. We don't even know who she is. But somebody set up that simulation. They did it to figure out, what you would expect from an 80% free throw shooter for 50 attempts. All right, so that's kind of what they would have stated. All right, they had a goal for setting up the simulation, try to figure out how this probability is going to function. Okay, then they planned how to do it. We can do it by flipping coins, rolling die, using calculators, just picking slips out of a hat, you name it. Okay, so you kind of figure out how you're going to pull off this simulation, then you do it, and then you witness what happens, and then you draw your conclusions, you communicate them, and so forth. Okay, there is a simulation coming up in application 4.1 which will kind of get your feet wet into it, and then I plan to do a supplement to this video where I'm going to kind of highlight a couple of simulations for you to think about. All right, so now look, I know I just kind of went through all of those kind of rapid fire. If for some reason you need to pause, then you need to pause. Then you can pick up after you've paused. So, application 4.1, will the train arrive on time? So your New Jersey Transit claims that its 8 a.m. train from Princeton to New York has a probability of 0.9 of arriving on time. So it's got a 90% on-time rate. Assume for now that this claim is true. Okay, the minute that they say something like that, it kind of makes you think, maybe we're going to be looking for evidence that it's not true. Anyway, explain what a probability of 0.9 means in this setting. So read and think about how I answered this, because a question like this is very common in this particular section. And the answer to it is going to follow the same sort of pattern from question to question to question that's like this. And the only thing that's going to change is the context. Like here, it's the New Jersey Transit. In the front page, it was Mrs. Gallus shooting free throws. Whatever it is, the context changes, but how you interpret the probability doesn't. So the answer is, if you take a very, very large random sample of the 8 a.m. Princeton to New York trains, all right, sounds a lot like probability or law of large numbers. About 90% of them will be on time. All right, so the 8 a.m. train has arrived on time 5 days in a row. What is the probability that it'll arrive on time tomorrow? Explain your answer. Okay, this is going to highlight sort of a fallacy in people's probability reasoning, and it's going to be called the law of averages. And if you're a sports enthusiast and you watch a lot of sports on TV, you're going to hear those sportscasters throw that phrase out. You know, if there's a batter that's a fairly good hitter, but they're in a slump, they'll say, well, this batter is due for a hit based on the law of averages. No. Whatever the probability is that that guy's going to get a hit, it's the same every time he goes up to bat. It's just like if you're planning to have 5 kids, and boom, 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 4 of them are girls. Well, does that change the probability that the last kid is going to be a boy? and make him more likely to be born? It's always 50-50, and if that fifth kid is a girl, try explaining to that girl, well, you beat the odds because it's somewhat less of a chance of you being born, less than 50%, just because your sisters were born ahead of you. No, that never changes. So here, the probability the train will arrive on time is still 90%. And the short term, the 5 days where it didn't arrive, doesn't have any impact on what that six day is, how the performance of the train is going to be. It's just weird that you saw 5 days in a row with late trains, but probability won't change just because that happened. All right, we're going to go a little more into this law of averages in that future video. All right, so a businessman takes the 8 a.m. train to work 20 days in a month, and he's surprised when the train arrives late in New York on 3 of the 20 days. Should he be surprised? Okay, now I'm just going to answer that right away, and then we'll kind of throw in some extra stuff. But if what the Transit Authority is saying is true, and there's a 90% on-time rate, that means 1 train out of every 10 is supposed to be late, right? So that means 2 out of 20 is supposed to be late, based on, what they're saying and what they're claiming. All right, if it shows up 3 times out of 20, which is almost 2 times out of 20, should that businessman be surprised? And the answer is no, because that's really close to what you would expect it to be. And there's just basic variation from sample to sample to sample, like we saw with Mrs. Gallus's free throw shooting. Okay? Anyway, to help answer this question, we're going to perform a simulation to estimate the probability that the train would arrive late on 3 or more of 20 days if the New Jersey Transit claim is true. All right. How would you use a 10-sided die to perform 1 repetition of this simulation? All right, since there's a 90% chance that this train is going to be on time, that means there's a 10% chance it will be late, right? So we need to take the numbers that we have on this 10-sided die. We'll assume it's 1 through 10, and we need 90% of them, if they turn up when you roll it, to represent a train that's on time. So the numbers 1 through 9, if that shows up on the die, will represent an on-time trip. And then the final 1 out of 10, which is the number 10, will represent a late train. So every time a 10 shows up, whoops, that's a late train. You roll the die 20 times to simulate 20 train rides, and you keep track of the number of late trains. Make sense? So the dot plot shows the number of days on which the train arrived late and 100 repetitions of the simulation. All right, every dot, like the one I circled here, that's a simulation of rolling this die 20 times and seeing 7 late trains, right? Then all of these dots represent, a 20 roll simulation, and this is the number of 5 out of 20 days where it was late, and then 4 out of 20, 3 out of 20. These are the number that this column here represents all of the times the simulations showed no late arrivals. Okay? So explain what the dot at 7 represents. It represents 1 repetition of the simulation. Remember, there were 100 repetitions where the train was late 7 out of 20 days. Sorry, I'm letting that cursor get in the way. Okay, so there's a lot of watching the trains, or at least simulating 20-day periods. So use the results of the simulation to estimate the probability that the train will arrive late on 3 or more of 20 days. Okay, I'm not going to count them, and I'm going to spare you having to count them. It's just this range of outcomes, all right? 3 or more. And it turns out if you count all those little dots, it's 30 out of 100, or 30%, 0.30, 0.30. Okay? All right. 30% is not that uncommon if their claim is 2 out of 20 days. Okay? So based on the actual result of 3 late arrivals in 20 days and your answer to the question 5 that we just showed, that the train will be late 3 or more days out of 20 when the train is on time 90% of days, there is not convincing evidence that the company's claim is false, because it's likely the train will be late 3 or more days out of 20 based on this simulation, given that it's an on-time rate of 90% of the days. Okay, so there it is. Wherever you need to pause and jot this down, do it. Like I said, stand by for the next video, which is going to be a supplement to this. I'm going to try to get to some homework answers and maybe explain some of them. Yeah, so stay tuned and we'll see you next time.